So, analysing circuits using Laplace transforms. We're going to spend a short time now introducing it. That's going to be this little video clip, and then over the next few weeks we'll be looking at some examples how we can use them to look at circuits. We're going to think about what they're used for, what they are, and how we use them. We're going to look at analysing circuits like this. The overall aim of these next few weeks is to look at circuits like this and think about what's going to happen to this circuit when I switch it on. What happens when what's happened to that toolbar up there? I want the magic pen button. That's all gone. Magic pen. Okay, so what happens when I close this switch and I put a voltage, and sorry, initially the capacitor is charged, so I initially charge it up and I close this switch. What happens? Instantly, as soon as that happens, and then some effect will happen, and then it will die away to some steady state. So we have this like transient period. What happens initially when I put something or do something to this circuit, and that's what this is about. We need a mathematical model to describe it, okay, and that's what we're going to be looking at, and using Laplace transforms to do it. So if I'd done this to this circuit, if I'd closed this circuit like that, and initially the capacitor was charged, so it might start off somewhere like that. Initially it's charged up. Sketch what you think will happen in this circuit over time. So a mathematical model that involves a change almost invariably means solving a differential equation. And last year, those of you who did the maths with me in year 2, we looked at differential equations. For this particular circuit, there's a differential equation that describes it, and here it is. And I want to look at this differential equation for a minute and talk about what it's telling us. Right, first of all, a reminder of some of the calculus that's involved here. This bit. Ben, if I were to say that in words, what would I say? The rate of change, the differential of q with respect to t. dq by dt for short. The rate of change of charge with time. That's what it means. The differential of charge with respect to time. What's the rate of change of charge with time? And if I were to plot a graph of charge against time, which you've just done, okay, then it would be telling me the gradient of that curve. So if I were to plot the thing, and I don't know what you plotted, but I'm not saying this is right or wrong, say it looked like that, then at any time t, the gradient of that curve would be the rate of change of charge with time. And that's what this means here, dq by dt. What's another name for the rate of change of charge with time in a circuit? The rate at which charge is changing with time, the rate of change of charge with time is called the rate of flow of charge, to give you a hint. May it be noted on the video that the class has no idea at all what the rate of flow of charge in an electric circuit is. Current. You knew that really, didn't you? Okay. The rate of flow of charge with time measured in amps. 1 amp is 1 coulomb per second. The rate of flow of charge. So in other words, this is another name for the current. So this is the current. That. If I multiply by the current by the resistance, what do I get? The volts. And that's what this is telling me here. Look. This is the voltage across the resistor. dq by dt is telling me the current, so therefore times that by the resistance, I've got that. So what I have here is this measured or written in a way that we can solve it as a differential equation. So this is a differential equation. All it is, though, is this. And if we look back at this circuit on the previous page, here, what's the voltage at any given time in this circuit? If I added all the voltages in here, what would it come to be? Sorry, Josh? 0. Good. Because there's no supply. Yeah, there's no voltage across it, is there? So if I add the voltage across this to the resistor, to the voltage across the capacitor, to the voltage across the inductor, at any given moment, they'd add up to 0. And isn't that what this is saying here? The voltage across the inductor plus the voltage across the resistor plus the voltage across the capacitor is 0. And what I've started to do here is write this voltage across the resistor in terms of charge and time. I'm after an equation that relates the charge and the time in this circuit because I want to sketch how the charge varies with time. So I need everything in terms of charge and time. And so I'm designing a differential equation that will describe it. And here it is. This bit's okay, isn't it? Is the voltage across the capacitor given by the charge divided by the capacitance? What's the equation that's involved there? Do you know it? Q equals CV. Charge across the capacitor is capacitance times the voltage. So Q divided by C gives the voltage. So that's okay. And that's okay. What about this one then? That's an awkward one. Anybody know a formula for the voltage across an inductor? Mr. Betts has got his fingers crossed at this moment in time. Voltage across an inductor is given by L Let's think about this. If the current was steady in this circuit, would there be an impedance due to the inductor? Answer, no. What is it that causes the inductance? Yeah, but what's that frequency changing? The voltage or the current, yeah. So if the current is changing through this inductor, we get this induced EMF. So if there is no change in current through this inductor, what's the voltage across it? Or what's the impedance of it, rather? 0, right. So, oops. So what's the formula for the voltage? Isn't it the inductance times the rate of change of current? Isn't that something that you've seen before? Yes? The rate of change of current times the inductance gives me the voltage. But the current is dq by dt. So it's the second differential. This is the second differential. This is equivalent to di by dt. Because I equals dq by dt, then di by dt equals the second differential of the charge with respect to time. So this is the voltage across the inductor, this part of this part here. If I can solve this, and that's what solving differential equations is about, and the way we're going to do it is Laplace transforms. If I can solve this, I can end up plotting the charge against the time across that circuit, and I can see whether or not this sketch is correct, okay, whether what we've done is correct. So let's have a look at it. There is my differential equation. The solution to this second order ordinary differential equation gives a function q as a function of time, which describes how the charge varies with time in this circuit. As we've just been saying, we're going to use Laplace transforms to find the solution. Just a word on this as a reminder from last year. It's second order because we've got a second differential in here. And it's ordinary because we've only got one independent variable, time. And it's a differential equation because it's got differentials in it. So it's a second order ordinary differential equation. And it's equation because we've got this equals 0 in there. So there it is. And then we're going to look at the Laplace transforms. We're going to play around with how they work. And then we'll end up with a solution. And here it is. There, on the next page. Now, if we look at it, we can see that the charge, and what I should have put here actually, is this, because it's a function of time. The charge at any given time t equals what's this bit? What does the Q0 mean, do you think? Sorry? Not the fundamental, but yeah, the initial charge at time 0, yeah, the initial charge. The instant I turn it on, what's the initial charge? Okay. This is some sort of exponential. We've just been looking at them. Which one is it? Of the three we're looking at in the drill, which one is that? It's an exponential decay, okay? And if I think about the number that goes in front of a cosine function or a sine function, which is what this is, what's that? What does the number in front of a sine or a cosine function tell us? Sorry? The magnitude, right. It's not a fixed magnitude. This magnitude, this amplitude, is a function of time, and there it is. So that means the amplitude of this wave is going to be decaying, an exponential decay. And then we've got some sort of cosine and sine part to it. So would you like to review what you think your wave is going to look like now, in the light of that? That's what it'll look like. I don't know whether that's what you got plotted. I actually put this into autograph, this equation, and it's there. And that's, apart from the fact I have to write it in slightly differently into autograph because it only recognizes y and x as the variables. That's typed in exactly what this solution was here. This solution there is what I've typed into autograph. It's got some sort of sine and cosine associated with it, so it doesn't necessarily start at 0. And so we can see in that case it doesn't, it starts up here. But it's going to oscillate with some sort of wave function. What it's saying is, if we look at this circuit and just think about it for a second, that's the charge flowing one way round the circuit, that's the charge flowing the other way round the circuit. So in fact, if you think about the circuit, the charge is flowing one way and decreasing, but then starting to flow the other way around the circuit, reaching a maximum value, dropping to 0, and then flowing the other way around the circuit. If you think about the mechanical equivalent, some sort of oscillating mass could be considered, might behave the same way. And charges in electric circuits do the same thing. So the charge is flowing first one way and then the other way around the circuit. And this oscillation, the amplitude of it is dying away to 0. So if I close this switch and left it for a period of time, what would be the current in the circuit? 0, right. So I'm only looking at the transient period. What's happening when I first turn this thing on? I'm going to get an oscillating charge that dies away to 0. What about the frequency of this oscillation? Could we get that from this? it changing? From there to there, or from there to there, or from there to there? Looks like the period is staying the same, isn't it? Okay, so the frequency of oscillation is the same, and we can work out what that frequency of oscillation is from this solution. So we can describe this function. We can say a lot about it. We can say what the initial charge or current rate is, the rate of change of charge with time, and we can say how long before it falls to a steady state, which we might well be interested in, this transient period. Nearly there. I just want to talk very briefly about how we're going to do it, and we're going to start thinking about this next week. How do we get from the ordinary differential equation to the solution, that magic solution that I just presented you with? We use these Laplace transforms. Generally, solving these ordinary differential equations uses integration, and last year we did some of that. How do you get back from a differential to the ordinary function? You integrate. That involves things that look like standard integrals on a table. All the techniques we looked at last year were about getting an integral to look like one of these standard integrals in a table, and then we could do it. Okay? This is not so dissimilar to that. What we do is we use Laplace transforms, which is an extension of this. We transform each part of our ordinary differential equation into a function involving a new variable called s. Like playing around with the integration to get it to look like a standard integral. Like setting up the original integral. And then we manipulate the function in S space, like playing around with the integral, using partial fractions or something like that, okay, to get it to look like a standard integral. Now we play around with this thing using algebra to get it to look like one of the S functions that we'll see in a table. So you get a table of these things. We get it to look like one of them. And then we can transform back and write down our solution. And that's what we're going to do. So you'll have a table of transforms. You'll get your function, turn it into this new S space, play around with it. That's the fun bit with algebra. Okay? And then we transform it back again. And bingo, there's your solution. So here comes the fun bit, okay? Algebra. Remember perfect square technique? We haven't talked about that much, I don't think. We certainly looked at partial fractions last year. So, oh look, we're going to be looking at these again and playing around with them.